Welcome, everyone, to this first module of our course on fluid flows for chemical engineers. In this module, we will lay the foundation for understanding how fluids behave, how they move, and how we can analyze and control them in chemical engineering systems. The principles we discuss today are not abstract textbook ideas, they are the basis of designing reactors, pipelines, distillation columns, heat exchangers, pumps, and countless other equipment that chemical engineers rely on every single day. Our journey begins by exploring the properties of fluids, both liquids and gases, and how these properties dictate their motion. From there, we'll move into the study of fluid statics and then dynamics, distinguishing between different flow regimes, such as laminar and turbulent flow. We'll explore how fluids behave in pipes and channels, why pressure drops occur, and how engineers handle real-world complications such as friction and energy loss. We'll also examine non-Newtonian fluids, materials that don't follow the usual rules of fluid motion, like polymer melts, blood, and slurries, since chemical engineers deal with them often. By the end of this module, you should be able to describe, in practical terms, how fluids move, what forces are acting on them, and how engineers apply these principles in designing safe and efficient systems. Section 1. Properties of fluids. Let us begin with the most basic but essential question: what is a fluid? A fluid is a substance that deforms continuously under the influence of a shear stress, no matter how small that stress may be. This definition includes both liquids and gases. Unlike solids, fluids do not resist deformation, they flow. The key properties that govern fluid behavior include density, viscosity, compressibility, and surface tension. Density is the mass per unit volume of a fluid. It determines how fluids respond to gravity, buoyancy, and pressure. For example, crude oil is less dense than water, which is why oil floats in oil-water separation tanks in refineries. Viscosity measures a fluid's resistance to flow. Honey has a much higher viscosity than water, which explains why it flows more slowly. In chemical industries, viscosity is critical. It influences pumping power, heat transfer rates, and even mixing efficiency. Compressibility describes how a fluid's density changes with pressure. Liquids are mostly incompressible, but gases are highly compressible, which is why handling gases often requires different tools and safety considerations compared to liquids. Surface tension is the force that causes a liquid surface to behave like a stretched elastic sheet. It plays a major role in processes like distillation, foaming, bubble formation, and droplet behavior in sprays. Understanding these properties is the first step in predicting and controlling how fluids behave in engineering systems. Section 2. Fluid statics. Before we look at moving fluids, let us pause and consider fluids at rest. This is the domain of fluid statics. Even when a fluid is stationary, it exerts forces, and these forces are of practical importance. In fluid statics, pressure is the key concept. Pressure is simply the force exerted per unit area, and in fluids at rest, it increases with depth due to the weight of the fluid above. This is why deep-sea submarines need extremely strong hulls. They must withstand enormous fluid pressures. Chemical engineers deal with fluid statics when designing storage tanks, pressure vessels, and pipelines. For instance, knowing how pressure varies with depth allows engineers to predict how much pressure a tank wall must resist and how strong the material needs to be. Another practical aspect of fluid statics is manometry, the measurement of fluid pressure using columns of liquid. Though more advanced sensors are common today, manometers remain useful for calibration and educational purposes. Section 3. Basics of fluid dynamics. Once a fluid starts to move, we step into the world of fluid dynamics. In dynamics, we analyze forces and motion together. Chemical engineers are less concerned with the exact mathematics and more with practical outcomes like flow rates, pressure drops, and energy consumption. One of the first assumptions we make is the continuum assumption. Although fluids are made of molecules, in most engineering situations we treat them as continuous matter, ignoring their molecular nature. This assumption allows us to talk about velocity, pressure, and temperature as smoothly varying quantities. An essential idea in dynamics is the concept of a flow regime. The two primary regimes are laminar flow and turbulent flow. Laminar flow is smooth and orderly. Fluid layers slide past one another with little mixing. This usually occurs at low velocities or in highly viscous fluids. An example is oil moving slowly through a narrow pipeline. Turbulent flow is chaotic and involves intense mixing of fluid elements. It occurs at higher velocities and is much more common in industrial processes. Turbulence increases mixing and heat transfer but also leads to higher energy losses. The transition between laminar and turbulent flow is not random, it depends on fluid properties, velocity, and characteristic dimensions of the flow. Engineers summarize this balance in what is known as the Reynolds number, but for now, simply note that it is the critical tool to predict flow regime. Section 4. Flow in pipes and channels. Most of the time, chemical engineers care about how fluids flow through confined geometries such as pipes, tubes, or channels. This is because virtually every plant uses piping networks to transport raw materials, intermediates, and products. Inside a pipe, the velocity of a fluid is not uniform. Due to friction at the pipe wall, fluid layers near the wall move more slowly than layers at the center. This creates a velocity profile, which depends on whether the flow is laminar or turbulent. Understanding velocity profiles is essential for designing pumps and predicting heat transfer. As fluids move through pipes, they lose energy due to frictional resistance. This manifests as a pressure drop along the length of the pipe. Engineers must calculate these pressure drops to ensure that pumps provide enough driving force to maintain desired flow rates. Undersized pumps may lead to insufficient flow, while oversized pumps waste energy. In addition to frictional losses, fittings such as elbows, valves, and expansions introduce minor losses, which can add up significantly in large plants. This is why piping layout and design are so crucial in chemical process engineering. Section 5. Dimensional Analysis and Similarity. Before diving deeper into specific flows, let's step back and look at dimensional analysis, a powerful tool engineers use to simplify fluid problems. Instead of solving complex equations for every new system, engineers identify dimensionless numbers that capture the essential physics. These dimensionless numbers include the Reynolds number, which tells us whether flow is laminar or turbulent. The Froude number, which describes the role of gravity in free surface flows like open channels. The Weber number, which characterizes the balance between inertia and surface tension, especially in sprays and droplet formation. By using these numbers, engineers can build small-scale models, run experiments, and then scale the results up to full-size industrial equipment. This approach is invaluable in chemical engineering, where building and testing full-scale plants is rarely practical. Section 6. Boundary layers and flow separation. When a fluid flows past a solid surface, such as the inside of a pipe or the surface of a heat exchanger, a boundary layer forms. This is the thin region where velocity changes from zero at the wall to nearly the full free stream velocity. Although the boundary layer may seem like a minor detail, it has enormous implications. The thickness of the boundary layer affects heat transfer, mass transfer, and pressure drop. In turbulent flows, the boundary layer is thinner, which improves heat transfer but also increases friction losses. Engineers must balance these effects in design. Boundary layers also lead to flow separation, where the fluid detaches from a surface, creating eddies and vortices. This is undesirable because it increases drag and reduces efficiency. In reactors and heat exchangers, flow separation can even cause uneven heating or dead zones. Section 7. Non-Newtonian fluids. So far, we've described Newtonian fluids, those whose viscosity remains constant regardless of the applied stress. But many fluids in chemical engineering do not behave this way. These are non-Newtonian fluids. Examples include polymer melts, paints, blood, toothpaste, and slurries. Their viscosity changes depending on the shear rate. Some become thinner when stirred, such as ketchup, while others become thicker, like cornstarch suspensions. Handling non-Newtonian fluids poses unique challenges. Pumping power, mixing efficiency, and flow predictions all require special considerations. In the food industry, for example, chocolate and yogurt are classic non-Newtonian fluids, and understanding their flow behavior ensures quality and efficiency. Conclusion of Module 1. To summarize, in this first module we have built the foundation for understanding fluid flows in chemical engineering. We started with the basic properties of fluids: density, viscosity, compressibility, and surface tension. We then explored fluid statics, looking at pressure and forces in stationary fluids. From there, we moved into fluid dynamics, examining flow regimes, velocity profiles in pipes, frictional losses, and the importance of boundary layers. Finally, we addressed the complexities of non-Newtonian fluids, which are particularly relevant in industries dealing with polymers, food, and biological systems. All of these concepts come together in the practical work of chemical engineers. Whether you are designing a pumping system for a refinery, a cooling network for a power plant, or a mixing tank for pharmaceuticals, the principles of fluid flow guide every decision. In the next module, we will shift our attention from fundamentals to applications. We'll study how fluid flow principles are applied in pumps, compressors, mixing, fluidization, multi-phase flows, and even advanced computational fluid dynamics. By the end of that module, you'll see how the theory of fluid flows connects directly to real-world chemical engineering practice.